So let's look at ionic bonding with Lewis symbols. So let's draw Lewis symbols for potassium and chlorine. How many valence electrons does potassium have? Just one, because it's in group 1. So there's the Lewis symbol for potassium. And for chlorine, how many does chlorine have? It's got 7. So there's 2, 4, 6, 7. Neither of these atoms has an octet. So what can they do? Well, we should know from our study of nomenclature that when we have a metal and a nonmetal, they're going to form an ionic compound. So what's going to happen is that potassium is going to transfer its 1 valence electron to chlorine. Okay, and when it does that, now how many valence electrons does chlorine have? It's got 8. Chlorine is happy. It also has a -1 charge. When we're doing Lewis symbols for negative ions, we put brackets around the dot part, and we put the negative sign on the outside. Otherwise, that negative can get kind of lost in the dots. Kind of calls attention to it. And this potassium has a positive charge. Now, in the Lewis symbol, it doesn't look like this potassium has an octet, does it? But if we look at the electron configuration, here's the electron configuration for potassium. This is the valence electron, right here, the 4th level, right? When we take that electron away, then in the electron configuration for the ion, the 3rd level is now the valence level. So these are the new valence electrons. They got promoted. Actually, they didn't really change at all. It's just the guy above them left, so now they're senior. They're the high ones. I think of this a little bit like if you had an onion and you can peel layers of the onions off, right? And so here we have an onion with this partial layer. There's just this little chunk on the side. We take that off, and what's underneath is a nice complete layer of onion, okay? And we could peel all of those off and have another layer of onion underneath, and you can just keep peeling and peeling. But usually we're just peeling off that incomplete layer on the outside. So potassium and chloride now are both happy with 8 valence electrons. Their opposite charges cause them to be very attracted to each other, and they form an ionic compound. Any questions? Let's use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. I did this with colors yesterday. I'm not going to do it with colors today because that got really tedious. Okay, magnesium. How many valence electrons? 2. 1, 2. Nitrogen. How many valence electrons? 5. 1, 2, 3, 4, 5. Now, I could put, there's going to be one side that's got a pair. I could put that pair anywhere. It doesn't matter. Top, bottom, right, left, it doesn't matter. But for nitrogen, I should have 3 electrons that are not paired and 2 that are paired up. And I'll just draw them to be convenient. Okay, so in Mrs. K's chemistry land, you know, atoms are alive and they have feelings and stuff, and they talk. And so here's magnesium, and magnesium wants to get rid of these 2 valence electrons because he's trying to get 8 and look like one of the cool noble gases. And nitrogen is wanting to gain 3 electrons so that it can have 8. And you can think of it this way too. For magnesium to get 8 electrons by gaining, it would have to gain 6 electrons. Gain 6, lose 2. Well, it's closer. It's easier to just lose 2. And for nitrogen, it would either have to lose 5 or gain 3. Gaining 3 is easier. So magnesium is looking for somebody to take its 2 electrons, and the nitrogen is looking for the 2 electrons. So it's like, hey, we can get together and we can help each other out, right? So magnesium is going to give its 2 valence electrons to nitrogen. So we're going to move those over there. There's 1, 2. And we'll put them over here on the nitrogen. And now we've got some charges going on. Magnesium now has a 2+ charge. And what's the charge on this nitrogen? 2-. Is everybody happy? Everybody got an octet? No. Magnesium's good, nitrogen not so much. So what does nitrogen do? He's looking for somebody else. If there's one magnesium atom around, there's probably some more. So enter another magnesium atom.
In other words, nitrogen's a hoe.
Hmm?
In other words, nitrogen's a hoe.
Yes, nitrogen's a hoe. And take his electrons anywhere she can get them. So here's a magnesium looking to get rid of 2 electrons, and this nitrogen wants one more. He's like, hey, take these electrons off my hands. And the nitrogen says, well, I'll take one of them, but then I'm full and I don't want any more. He's like, well, that's better than nothing. So this magnesium will give 1 electron to the nitrogen. And then that changes the charge here to 3-. Now we've got a happy magnesium ion, a happy nitrite ion, and 1 not so happy magnesium ion. So if there's 1 nitrogen around, there's probably another one around. So let's bring in another nitrogen atom. 1, 2, 3, 4, 5. Magnesium looking to get rid of that electron. Nitrogen's like, I'll take that off your hands. Cool, awesome. Done deal. Now the charge on this magnesium's 2+. That magnesium's happy. Peeled off its valence electrons, full shell underneath. This nitrogen now has a -1 charge. Is the nitrogen happy? No. This nitrogen is looking for 2 more electrons. Well, we're going to have to pull in another magnesium atom with 2 electrons on it, 2 valence electrons. It's all about the valence electrons. So nitrogen says, hey, I need 2 more valence electrons and you're trying to get rid of 2. Let's help each other out, right? This reminds me of trying to play Hot Wheel cars with little boys, right? And the cars talk to each other. I was never good at that, but I can make atoms talk to each other. I'm not sure why that is. So this is 2+ now, and this nitrogen is 3-. Is everybody happy? Yeah, everybody's happy. When we did this with potassium and chlorine, it seemed easier. Potassium gave 1 electron to the chlorine, and then we were done. This is a little more complicated.
These potassium and chlorine are, monogamous and respectable.
Yes. Potassium and chlorine are monogamous and respectable, yes. And these guys not so much. They're catting around. Okay, so we did all of this. We got to get back to what we were trying to do, predict the formula. Well, now we can look at this. I've got 1, 2, 3 magnesium ions. So it's going to be Mg3. And I've got nitrogens, and I've got 2 of those. So this is the formula that we predict by transferring valence electrons using the Lewis model. Now we have looked at predicting formulas for ionic compounds before, but we did it in a different way, right? We looked at magnesium on the periodic table and we said it's in group 2, it's going to have a +2 charge as an ion. And we looked up nitrogen and we determined from the location on the periodic table it's going to have a -3 charge. And so we looked at Mg2+ and we looked at N3-, and we said, well, how do we combine those so their charges add up to 0? We end up with the same answer, we just got there thinking about it in a different way. Doing it this way, just looking at the charges to get the formula, is faster. And so that's what we actually just do. But this explains why it works. Any questions? Well, if we look at the reaction between sodium, the element, and chlorine, the element, they will react quite exothermically to form sodium chloride. The enthalpy of formation standard enthalpy of formation for this is minus 411 kilojoules per mole. So 1 mole of sodium chloride forming releases 411 kilojoules of energy. Well, where is this energy coming from? Well, we've talked about ionization energy and electron affinity. And what's happening here is this sodium has 1 valence electron. It's transferring its valence electron to a chlorine atom. So that's an ionization energy for sodium. It requires 496 kilojoules of energy to be given to sodium to pull that 1 electron off. Chlorine has a negative electron affinity. When you give it an electron, it releases 349 kilojoules of energy. So if we add these two together, we end up with positive 147. That means that transferring an electron from sodium to chlorine actually absorbs 147 kilojoules of energy. Well, then why does this reaction release energy? There's got to be something missing here. We can't just look at ionization energies and electron affinities. The thing that's missing is lattice energy. Lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions from gaseous ions. Electrical charges are a little hard to visualize, and so I always kind of translate them into magnetic things. If you've got north and south poles of magnets, they're just going to click together. You get them close enough and it'll just happen spontaneously, right? So I imagine a whole bunch of magnetic marbles just going click, 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 and they'll all clump up together. Did I have to do anything to make them do that? No. It's the attraction between these opposite magnetic fields. For ions, it's the opposite. I need to learn how to talk. Yeah. For ions, it's the attraction between oppositely charged ions, and they just are attracted to each other. The potential energy of them is lowered when those opposite charges come together. If the potential energy is lowered, then that energy must be released in some way. It has to go somewhere. It's released as heat. So this is an important idea. The formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. I talk about it that way. I will continue to talk about it that way. It helps us to understand what's going on, but it's not the driving force for the formation of an ionic compound. The driving force is that after that electron transfer occurs, the positive and negative ions are very much attracted to each other. And when they coalesce, when they come together to form a lattice, a great deal of heat is released, a great deal of energy. So the driving force is the attraction of those oppositely charged particles. Here's a kind of an illustration of that. So if you think of sodium ions and chloride ions in the gas state, and they're going to be attracted to each other, and they're going to go whoosh, and whoosh. I don't have a good sound effect for that. And they're going to make this, right? And this has these little red smoky things off of it because it's releasing the energy as heat when those things come together. So we could take this into like a relationship analogy. So if you think about two people that are really, really attracted to each other, right? Maybe they see each other one night across a crowded room, you know, and they're really attracted, and then when they come together, things get hot. Right? Maybe? So,
Dr. K used the same analogy between you guys.
Pardon me?
I think Dr. K used the same analogy between you guys.
Did he? Did he? Yeah. Well, that's kind of what happened. Yeah. We saw each other across the room on the first day of graduate school, and there was attraction, and chemistry happened.
You two bonded?
We bonded, yes, and we now have a triple bond because we share 6 electrons. Yeah, it's Good thing it wasn't 7 because that would have been awkward. So how can we calculate this lattice energy, this heat that's released? The easiest way is to use what's called a Born-Haber cycle. This is a hypothetical series of steps that represent the formation of an ionic compound from its constituent elements. So the principle under this is Hess's law, where you can take different chemical reactions and add them together. Do you remember that? And get the total reaction. And then you look at the enthalpy changes for each of the steps and you add those together and you get the overall enthalpy change. Okay, so that's what we're going to do. So here is a Born-Haber cycle for the reaction of sodium and chlorine to form sodium chloride. So this is the starting point right here. When sodium and chlorine react to form sodium chloride, the product has lower energy than the reactants. And so this energy is released. Delta H is negative for this reaction. We can look at what the lattice energy is by looking at what else is going on. So we'll take sodium solid and make it into a gas. Well, you have to put in energy for that. And then we're going to take this chlorine molecule, half of a chlorine molecule, and make it into a chlorine atom. Well, that's also an endothermic process. You have to put energy in. And then we're going to take the sodium ion and pull off its valence electron. That's endothermic. You have to put energy in. Then we'll take the chlorine atom and give it an electron. Chlorine has a negative electron affinity, and so that's exothermic. And so now we've got the sodium ion and the chloride ion in the gas state. And the difference between this point and the final is the lattice energy. These other steps can be measured. This overall enthalpy change can be measured. Each of these steps can be measured. They're available. You could Google them and find them, or you can look them up in the CRC. And so you find the lattice energy using adding and subtracting. Questions? There are trends in lattice energy. One of the trends has to do with ion size. So here's a table showing different metal chlorides. These are all alkali metals in group 1. So lithium, sodium, potassium, cesium in a compound with chlorine. And we see that the lattice energy, as we go down that group on the periodic table, the lattice energy becomes less negative. It becomes less exothermic. So that means the attraction, the energy released when these guys come together is less. And it has to do with ion size. So here we have illustrations of ion size. The chloride ion is the same for all of these, but lithium is the smallest ion and cesium is the largest ion. We learned that in our periodic trends, that things get bigger as you go down. Well, if cesium is larger than lithium, that means the distance between the cesium nucleus and the chloride nucleus is going to be larger, 348 picometers compared to 241 picometers. If they're farther apart, they're going to be less attracted. We can refer back to Coulomb's law. The energy is proportional to 1 over r, where r is the distance between the charges. Well, the distance between the charges is bigger here. You can kind of think of this as maybe people being attracted to each other, but here this guy's wearing a Speedo, and maybe this guy's wearing jeans, and this guy's got a parka on, and this guy, he's got one of those inflatable sumo suits on, right? And you can't even see him. And so the attraction between these two is going to be less than for those. Does that make sense?
Say long distance can work.
So yeah, people say long distance relationships can work. They can, but they require a lot of energy. Yeah. I can turn anything around back to chemistry. Well, ion charge has an effect also. So here we're going to compare sodium fluoride and calcium oxide. If we look at the sizes, the distance between the nuclei for sodium fluoride and for calcium oxide is very similar. That's why we chose these two compounds to compare. So size isn't an issue here, but charge is. Sodium and fluoride each have a 1 charge, and calcium and oxygen are a 2 charge, +2 or -2. We see that the calcium oxide has a much larger lattice energy than sodium fluoride. Ionic size has been taken out of the picture. It's got to be the charges. Coulomb's law also says that the energy is proportional to Q1 times Q2. The charge on the one times the charge on the other. Well, for sodium fluoride, it's 1 times 1, which is 1. For calcium oxide, it's 2 times 2 is 4. So you predict that this would be 4 times as attracted as this one. And if you look at the lattice energies, and you take 910 times 4, would be 3640, and the actual is 3414. That's pretty close. It's roughly 4 times as big. So charge is important. Charge is actually a bigger factor than the radius, the distance. Any questions? So summary of the trends. Lattice energies become less exothermic with increasing radius, ionic radius, and more exothermic with increasing magnitude of ionic charge. So this is a sort of question that could show up on the next exam. Not the one today, but the one in a while. Yeah, if I put this on the exam today, that would teach those slackers that aren't here in lecture. Hopefully they'll watch this video later, but I don't know. Anyway.
Do you always have a surprise pop quiz that counts for half the
I do occasionally do stuff. I do. So, yeah. Okay, let's just do these. So we're supposed to take lithium bromide, potassium iodide, and calcium oxide and arrange them in order of increasing magnitude of lattice energy. So we want the one with the lowest lattice energy, the smallest, to the biggest lattice energy. So we have to think about size and charge. Well, let's look at charge. Here I've got potassium is a +1 and iodide is a -1. I don't know why I did that one first. And there's lithium is a +1 and bromide is a -1. And then we have our little friend calcium oxide here, +2 and -2. The effect of charges is often going to be the biggest factor, so let's look at that first. So which of these is going to have the largest lattice energy? The calcium oxide, because we have +2, -2. You multiply those, the product is -4, and these it's just -1. So on charges, we say that this one's going to be biggest. So I'm going to start out by just putting calcium oxide at the far right. We're going to increasing magnitude. So calcium oxide we think is going to be the biggest lattice energy. And by charge, these two would be tied. So then we're going to use size as a tiebreaker. Well, let's find these in the periodic table. So here's lithium and bromide. And then we've got iodide and potassium. So lithium and bromide are larger or smaller than potassium and iodide? Smaller. These are smaller. Comparing lithium and potassium, lithium is above potassium on the periodic table. Things get larger as you go down. Here, bromine and iodine, the bromine is going to be smaller. Smaller charges can get closer together, and so they're going to be more strongly attracted to each other. So we're going to put lithium bromide in the middle here, and potassium iodide is as the lowest. Because well, as we go down, the ion size increases, and so, iodine here is wearing a parka, and potassium has the sumo suit on. And here, bromine is just wearing a light sweatshirt, and lithium's here in shirt sleeves. Well, they're going to be more attracted to each other, if you like that analogy. Any questions? Always good to check that your model matches up with reality. So does this ionic bonding model match up or explain the properties of ionic compounds? Ionic compounds have high melting points. The model explains this because these ionic bonds are non-directional. In this solid sodium chloride, any one ion is attracted to ions on all sides. And so in order to melt this, you have to break a lot of attractions in all different directions. The solid compound does not conduct electricity because the ions are fixed in position, they can't move around. If you melt it though, if you heat it up so that it becomes a liquid, then the ions can move around and it does conduct electricity. We also see that the solid, should have pointed over here earlier. So this is the solid not conducting electricity. If we dissolve the solid in water, that allows the ions to separate and move relative to each other, and it also conducts. Any questions?
What's the sound effect of that?
What is the sound effect for that? That's an excellent question. I don't know. I don't have one today.